So now that we've looked at what a first derivative can tell us about a function f, now we're going to be taking a look at the second derivative. So in our kind of opening example here, we've got two functions shown below, and they're both increasing on this interval from a to b. So increasing this way, and we are still increasing this way. But what happens when we draw in the tangent lines? So if I were to take any point on this first interval, it could be here, could be here, could be here. Our tangent line would look something like this, or it might look something like this, or it might look something like this. If I do the same thing on this curve, and I pick any point in that interval, and I draw my tangent line in, my tangent line is going to look like this, might look like this, might look like this. You'll notice that depending on which way our graph was increasing, whether it was kind of going upward sloping or kind of like almost going upwards and almost downwards at the same time, our tangent lines happen to be in different spots. So on the first interval, or on the first graph, our tangent lines were actually below the curve. But when we drew in the tangent lines over here on the second graph, our tangent lines ended up being above the curve. And when this happens, this has to do with something called concavity. So the definition of concavity says that if the graph of the function f, so this some function f, lies above all of its tangent lines, so meaning if I drew the tangent lines below the curve, my f is lying above those tangent lines, then we would call the curve to be concave upward, or you'll see that abbreviated as CU on the interval. Over here, if our graph lies below all of our tangent lines, because our tangent lines were on top of our curve here, then we say that the graph of f, or the function, would be concave downward on the interval. So again, sometimes abbreviated CD. And you can almost kind of see that, like our graph is kind of sloping upwards, so we kind of have like a concave up. So our graph is almost kind of U-shaped here, and our graph is increasing, but it's kind of like facing downwards. This is concave down because we're kind of like almost having like a downward U shape. So the concavity has to do with our second derivative. So we know that our first derivative tells us where the function will be increasing or decreasing. The second derivative tells us about concavity. Is the function concave up, or is it concave down? So if our second derivative, our f double prime of x, is greater than 0, or if it's positive for all x in the interval, then we would say that the graph would be concave upwards, or concave up, or CU. If our second derivative, or if f double prime, is less than 0, so it's negative for all the x in the interval, then the graph would be considered concave down, or CD on the interval. And where concavity changes, so if we're going from concave up and the graph switches to concave down, or vice versa, if we're going from concave down to concave up, the point where we're switching concavity or changing concavity is called an inflection point. And we can say that f is continuous there, and we're gonna just kind of finish that off and say the curve changes from either concave up to concave down, or concave down to concave up, which basically tells us that our second derivative is changing signs. So we'll look at this graphically, and we'll look at this algebraically just to kind of see what this looks like in different instances. So we're going to take a look at the second derivative graph first. We'll be looking, I'm sorry, first derivative graph first, and then we'll be looking at a second derivative graph later. All right. So in this first example, we have some graph here. And what this graph is representing is the graph of the derivative of f. So we're looking at a derivative graph right here. And this derivative is consisting of these two semicircles and the two line segments over here. So we want to identify the critical numbers of the function f. So now we're looking for critical numbers of the original function. So basically we want to know where is the graph changing from increasing to decreasing and decreasing to increasing. So on the graph of the derivative, which we kind of investigated a little bit in the last video, we know, I kind of pull that in again, we know that if we're looking for the changes in the signs from positive to negative or negative to positive, we're really looking at the relationship to the x-axis. So above the x-axis here, this is telling us that our derivative is greater than 0, because that's where my f prime is above the x-axis. Down here below the x-axis, this is telling me that my derivative is less than 0. So basically, this is telling me that we're increasing up here at the top and we're decreasing down here at the bottom. Well, the point where that's changing is going to actually be the x-intercepts. Because if we're going from increasing to decreasing or decreasing to increasing, that's where our tangent slope is changing either from positive to negative or negative to positive. So in this case, if we're looking at the derivative graph, our critical numbers would be our x-intercepts. So we're going to list, even though we don't know what's kind of going on the other side over here, we're going to list the x is equal to -5 as a critical number. That would also be x is equal to -3. That would also be x is equal to 1. And x is equal to 4. So again, that's where we're changing from either going from positive to negative or from negative to positive. So then we want to identify the intervals on which the function f is either increasing or decreasing. So this again has to do with kind of the placement above or below the x-axis. So I'm going to go ahead and make myself a little sign chart here. And I'm going to label this as f prime because we're going to be making sign charts for our second derivative, just so that we're kind of able to tell the difference here. And I'm going to split up this number line as I kind of labeled the critical numbers up here. So I'm going to start at -5, I'm going to go to -3, I'm going to go to +1, and I'm going to end at +4. And I'm going to go a little bit further because we do have a section of the graph here that does follow after the x value of 4. So if we look at the domain here, the domain of our function would be -5 to +5. So I want to capture all those values in my sign chart. So from -5 to -3, our derivative is above the x-axis. So we're going to say that's a plus. -3 to 1, derivative is below, so we'll say that's minus. 1 to 4 is above, so plus. And then 4 to 5 is below, so minus. So this is going to tell us that we've got some intervals that are increasing. We definitely have some intervals that are decreasing. So we're going to say we're increasing from -5 to -3. And we're also increasing from 1 to 4, because that's where we're positive in our sign chart. We're decreasing from -3 to 1 and from 4 to 5, because that's where we're negative in our sign chart. So I'm just going to write here as a little explanation, since our f prime is positive, we're increasing, and then since our f prime is negative, we would be decreasing. Okay, so then we want to use this information to say, okay, well, where do we have a relative maximum? So up here, if we look at our arrows, we would have a maximum going from increasing to decreasing. So this would happen at two places, the x value of 3, and this would also happen at the x value of 4. So x is equal to -3 and x is equal to 4. And I'm going to say my explanation would be, since f prime changes signs from increasing to decreasing. Okay, so that's kind of a review of what we did in kind of the last piece with the increasing decreasing test. Now we're going to look for our second derivative piece here. So this next part is asking us for our point of inflection. So now I want to think about concavity. So I want to think about the second derivative here. So to find the second derivative, I want to think about the slopes of my first derivative, because if we want to get a second derivative from a first derivative, remember that we're really looking at slopes. Same as we would go from a function f to a first derivative, we'd be looking at slopes. So I'm going to use the slopes of f prime to determine something about the second derivative here. So basically, I want to look at my graph and determine, okay, well, where is my slope changing? So I'm going to go left to right. So I'm going to determine the intervals of increasing and decreasing of this f prime. So if I'm looking from -5 to -4, my slopes of my tangent line would be positive. If I'm looking from -4 down to, I guess, about probably -1, my slopes of my tangent lines would all be negative. And then if I'm looking from -1, probably up to 2, the slopes of my tangent lines anywhere along this segment would be positive. And then from +2 down to +5, all of my slope of my tangent lines would be negative. So basically, that's how I want to determine the concavity or the second derivative piece here. So I'm really looking at what are the slopes of the tangent lines? Are they positive? Are they negative? So now that I've kind of have those intervals identified, I'm going to label my number line using -4, -1, +2. Those are the places where the slopes of my tangent lines would be changing on my graph of f prime. So my f double prime, I'll make myself a number line. Again, I still want to capture the whole domain from -5 to +5, but I'm going to put in -4, -1, +2, and I'll put my ending domain value of 5. So again, the reason that I'm picking these values is if I'm going from -5 to -4, the slopes of my tangent lines would be positive. So I'm going to go ahead and put a plus from -5 to -4. From -4 to -1, my slopes of my tangent lines would all be negative. So I'm going to go ahead and put a negative from -4 to -1. From -1 up to +2, the slopes of my tangent lines would be positive. And then from 2 to 5, my slopes of my tangent lines would all be negative. So since we're talking about concavity here, like we put kind of little arrows indicating increasing and decreasing for the first derivative, what I like to do for my f double prime is actually make the concavity. We know that if f double prime is positive, we're going to be concave up. If f double prime is negative, we're going to be concave down. So what this means is that from -5 to -4, we're concave up. From -4 to -1, we're concave down. -1 to 2, concave up. 2 to 5, concave down. So basically, where this concavity is changing, the point of inflection is where concavity changes. So concavity is changing where the concave up goes to concave down, or where concave down goes to concave up. So the x values where this is happening would be x is equal to -4, x is equal to -1, and x is equal to 2, because that's where concavity is going from up to down to up, or an up to down. So I'm going to say f double prime either goes from increasing to decreasing, or positive to negative, or vice versa, decreasing to increasing. So negative to positive. So then if I want to identify the intervals where we're concave up, well, this little sign chart over here is really helpful for that, because now we know exactly that we are concave up, or CU, from -5 to -4, and from -1 to 2. And we are concave down from -4 to -1, because that's where we're minus here, and from 2 to 5. And I'm going to put for these my reasoning. So we're concave up since our second derivative or f double prime is positive, and we are concave down where our second derivative or f double prime is negative. All right, so let's look at the second derivative in terms of algebra. So we have a little second derivative test, which we'll kind of get into probably a little bit more after break. But just know that there is a second derivative test, and we'll see how that's really helpful for us. We're probably not going to get much into it in this example, but it does kind of go along with what we're talking about with the f double prime. So suppose f double prime is continuous near a value c. If the derivative of the function at that c value is equal to 0, and the second derivative is greater than 0, then we would say that f has a local minimum. So if our slope of our tangent line is 0 and our second derivative is greater than 0, then we have a local minimum. If our derivative at the c value is 0 and our second derivative is negative, then we would have a local maximum. So this is a second derivative test. Again, we'll kind of get more into this when we come back from break. So let's put this kind of all together and say that I want to graph this function without actually knowing what the graph looks like, without pulling out my graphing calculator and saying, okay, well, I can just look at it and kind of eyeball it. So we're going to kind of put everything together using the increasing decreasing test and using the concavity that we just talked about. So our first step is going to be to find the critical numbers here. So we want to take the derivative of this function, which would give us negative 3x squared minus 6x plus 9. Set that equal to 0. Factor out my GCF of negative 3. So x squared plus 2x minus 3. Factor that out. And it looks like my critical values or my x values would be negative 3 and positive 1. And now I want to use these critical numbers to determine, well, where is my graph increasing or decreasing? So I'm going to go ahead and set up my number line here. And I'm going to put my critical numbers in. So negative 3, positive 1. I'm going to pick some values in between here to test in my first derivative. First derivative, because we're talking about increasing and decreasing. So I'll do f prime of, let's do negative 4. So I'm just picking a value in this first kind of interval here. And I'm going to plug it into this first derivative. So negative 3 is negative. Negative 4 plus 3 would be negative. And then negative 4 minus 1 would also be negative. So that will give us a minus. Pick a value between negative 3 and 1. I'll do 0. That's easy. So negative 3 is still negative. 0 plus 3 would be positive. And then 0 minus 1 would be negative. So this ends up being a plus. And then from 1 to infinity, I'll just pick, I don't know, 2. So negative 3 is negative. 2 plus 3 is positive. 2 minus 1 would be positive. So this will give us a negative. So we're increasing and decreasing in these intervals. So now I can kind of go ahead and just summarize what my arrows are telling me. So we're increasing from negative 3 to 1, and we are decreasing from negative infinity to negative 3, and from 1 to infinity. So that's I'm going to go ahead and label that as my f prime. So that's what I'm talking about, the first derivative. So then I can determine, well, what are my local extrema? So I know that there's going to be a min happening at negative 3. And I'm going to go ahead and find out what that y value would be by plugging that back into my original function. Again, I can use a calculator here to help me out a little bit with my calculations. I believe that gives us negative 17. And then our max, if we kind of look back up at the sign chart, our maximum would be happening here at the x value of 1. And I will go ahead and find out what that y value would be again by just substituting it back into f, which would give us 15. So my min would be happening at f of negative 3 is equal to negative 17. My max would be happening at f of 1 is equal to 15. So then I want to find the points of inflection. So again, points of inflection is indicating that we want to take a second derivative. Well, I know what the first derivative is. We found that in part A. So I'm going to go ahead and algebraically find out what f double prime would be. So that would be negative 6x minus 6. And my points of inflection are going to happen algebraically. I'm going to go ahead and say, because it's not always going to be a point of inflection. So possible points of inflection would happen where our f double prime would be equal to 0. So I'm going to take this double prime and I'm going to set that equal to 0. So I believe that would give me 6 is equal to negative 6x. So a possible point of inflection would happen at the x value of -1. And it's only possible because we always have to go back and test it. There's a chance that concavity could be changing here, but concavity doesn't always have to change at that x value. So I'm going to go ahead and make myself a number line for my double prime. And I'm going to put my possible point of inflection in as kind of like my, almost like what we put in for the critical values up here. And what I'm going to do is pretty similar. I'm going to take values and I'm going to test the values on either side of that possible point of inflection to see if concavity actually is changing. So I'm going to pick a value and I'm going to plug into my second derivative. So on my first interval from negative infinity to -1, I'll do, I don't know, -2. And I'm going to put that back into my second derivative over here. So -6 times -2 minus 6. That will give me a positive 12 minus 6, which would give me a positive. So I'll put a plus in there. And then from -1 to infinity, I'll pick, I don't know, 0. So -6 times 0 minus 6 is going to give us a negative value. So what this is telling us that is our second derivative is going from plus to minus, which means that we are going from concave up to concave down, which means that concavity is changing at this x value. So if this was to go from up to up or down to down, concavity wouldn't be changing, and this wouldn't actually be an actual point of inflection. So to figure out what the point is, I know what the x value is. I'm going to go ahead and put that x value of -1 back into my original function. So similar to what we did for the max and the min, you always want to go back to your original f. So if I do that and I plug that in, I'm going to use my calculator to help me here because I actually don't have that worked out. Minus 3x squared plus 9x plus 10. That would actually give me -1. So my point of inflection is happening at f of -1 is equal to -1. So then this sign chart is actually helping me to answer the next part of my question, find the intervals where the function is concave up or concave down. So we are concave up from -infinity to -1, and we are concave down from -1 to positive infinity. So what I'm going to do is I'm going to kind of talk a little bit about the second derivative test. Like I said, we'll kind of get more into this after break, but I can actually confirm that my local extrema, so for part B, that these are the actual intervals where we should be increasing and decreasing. And basically what that's going to allow me to do is take these critical numbers, which we got of -3 and 1, and I'm just going to basically use the rules that I talked through up here. So we want to evaluate the derivative and the second derivative. So I'm going to go ahead and I'll do, I don't know, the second derivative first. I'm going to do f double prime of my critical number of -3. Double prime, again, is this -6x minus 6, which is 18 minus 6, which would be 12. And I'll do the same thing for my other critical number of 1. So f double prime of 1, -6 times 1 minus 6 will give me a -12. So basically what this is telling me is that we already know that the first derivative, or f prime of -3, is 0, because that was kind of where our increasing decreasing was changing. So we know that the second derivative at -3 is positive 12. We know that the first derivative of -3 is 0. Over here, we know that our second derivative at 1 is -12. And again, we would know that our first derivative at 1 would also be 0, because again, that's what the critical number is telling us. So using the second derivative test, what this tells us is that since these two things are happening, f double prime of -3 is positive and f prime of -3 is 0, is, that's a positive, and f prime of -3 is 0. This is telling me that if the second derivative is positive and my first derivative is 0, then we have a local minimum. Over here, our second derivative is negative of the x value of 1. And we know that our first derivative is 0. So if our second derivative is less than 0 and our first derivative is 0, then we have a local max. So that confirms what we said over here, saying that we have a minimum at -3 and we have a max at +1. So we'll kind of get more into those kinds of examples when we come back. So knowing what we know about all of this stuff from A to F, what we can actually do is we can sketch a graph of the function f. So meaning of this cubic function, not even knowing what this looks like in our calculator. So what I'm going to do is I'm just going to kind of draw myself a little coordinate plane here. And I know that my maximum has to happen at a y value of 15 and my minimum has to happen at a y value of -17. So I'm just going to kind of go and quickly just sketch in those high and low points. And then I also kind of need to put a little scale on my x-axis here. Just make some quick tick marks here. And I will put in my min and my max. So my min is at -3, -17. So I'll put a point down here. My max is at 115. So put a point up here. And I know the intervals of increase and decrease. So sometimes I find it's easier to kind of look for the interval that doesn't have the infinity in it. So I know that I'm increasing from the x value of -3 to the x value of 1. So basically where I just put those 2 points, the x value of -3 to the x value of 1, my graph should be increasing from here, which means that on either other side, they would have to be decreasing. So again, we read our graphs left to right, so we'd be decreasing and then decreasing. We know that this is some sort of cubic function too, so we know that it should be kind of curved as we're drawing it. But it's not enough to say, okay, I know where it's increasing, I know where it's decreasing. I also have to take into account the concavity. What this is telling me is that my graph is going to be changing from going from like an U shaping up to a U shaping down or vice versa at -1, -1. So I'm going to put in a little point of inflection here. So this is going to be where my concavity is changing. So I know we're increasing, but I want to know how we're increasing from -3 to +1. So we know we're concave up from -infinity to -1. So meaning basically at this point of inflection, everything to the left of it is going to be a U shaping up. That's what concave up means. We're concave down from -1 to +infinity. So at this x value of -1, everything to the right should be facing downwards. So if we kind of get an idea of what that's going to look like, and I'm just going to really draw a rough sketch here, that would look something like this. So we're concave up all to the left side of the x value of 1, and we're going to be concave down all to the right of this x value of -1, which also fits our intervals of increase and decrease. We know we're increasing from -3 to +1. Our graph is going upwards, and we know that we're decreasing everywhere else. Our graph would be going downwards. So even without knowing what this graph looks like on a calculator, we can kind of get a good idea of what it might look like just knowing about our second derivative and our first derivative and the tests that come along with that. And then if you wanted to, you could actually go ahead and graph that on your graphing calculator to kind of confirm that your sketch is pretty accurate, which we are relatively accurate here. All right, so let's kind of put this all together and say, okay, well, what if I have a graph, but now we're talking about the graph of the second derivative. So before we looked at a graph of the first derivative. So now we're talking about the graph of the second derivative. This is the second derivative of g, and we're working on the domain from -7 to +7. What I want to do is I want to say, okay, well, how do I identify inflection points? How do I identify intervals of concavity using a second derivative? Well, it kind of almost is the same as what we were looking at with the first derivative. If I'm looking for inflection points, I'm looking for where concavity is changing. Where is f double prime going from positive to negative or from negative to positive? Again, this is going to have to do with the relationship with the x-axis. We know that g double prime is going to be positive everywhere above the x-axis. It's going to be positive up here. Everywhere below the x-axis, my g double prime is going to be negative, or negative below the x-axis. So what I'm going to do is I'm going to say, okay, well, where am I going from negative to positive or positive to negative? Well, that's going to be happening at our x-intercepts again. So it looks like we've got some x-intercepts going on. We have a -5, looks like we have a -1, and then we have a +3. And what I'm going to do is I'm going to set up myself a little sign chart here of f double prime. And I'm going to include the interval from -7 up to +7. And I'm going to put these these x-intercepts in as kind of almost my like critical numbers, because that's where the sign of f double prime is changing. From -7 to -5, we're below the x-axis, so our double prime is negative. From -5 to -1, we're above the x-axis. From -1 to +3, we're above the x-axis. And then from 3 to 7, we're below the x-axis. So this is telling us that our graph of G, the original graph, would have inflection points in two places, because from -7 to -5, this is telling us that we are concave down. From -5 to -1, we're concave up. From -1 to 3, we're also concave up. From 3 to 7, we're concave down. So our points of inflection are only happening where our concavity is changing from negative to positive or from positive to negative. So our points of inflection here are only happening at -5 and +3 because concavity is not changing at -1. So that would not be a point of inflection. So to answer part one of our question over here, using this graph of the second derivative, find the inflection points on the graph of G. Well, our inflection points would be x is equal to -5 and x is equal to 3. And that's because that's where f double prime of x changes signs, or goes from concave up to concave down, or concave down to concave up, whichever the change is that's happening there. So then we can identify our intervals where we're concave up and concave down now that we kind of have that marked on our sign chart. So I'm going to write concave up. We're concave up from -5 to 3. And we're concave down from -7 to -5. And from 3 to 7. And I'm going to put since for concave up, since our second derivative is above the x-axis or we're greater than 0, and we're concave down since our second derivative is below the x-axis or our second derivative is negative. All right, so I'm going to have you guys work on some practice problems. Please let me know if you have any questions.